Hey, we are going. 7.3. Sampling distribution of X bar. Woohoo! Okay, so we're going to last time we talked about proportions, p hat. This time we're talking about X bar. We're going to do our SCS. We're going to do the easiest two first, and then we'll go to shape. Shape is a little complicated.
Of course it is.
Just a little bit. So we'll cover that one last. Yeah. All right, center. It's the easiest one. Okay, the average is the average.
Okay.
Mm-hmm.
Kind of like a word avalanche there.
Isn't it? And this right here is going to be the mean of the population. So I would really recommend that you write stuff down, take some notes on paper rather than on your electronic
You're adding the
devices.
people watching the video, not us.
Yes.
Yeah.
Of course. Okay, so this is the average that you would expect to get, right? So like you're going to do lots of samples, supposedly. I mean, whoever does more than one sample.
No one.
And no one does that, right? But if you did, the average you would expect to get should be the average of everybody. Which makes sense.
Yeah,
Yeah,
I get that. Right.
cool. And the spread, the standard deviation of the average you expect to get is going to be the true standard deviation of all the data divided by the square root of the sample size. And we'll identify this. So this is the standard deviation of the population. And every time we do standard deviation for SCS on sampling distributions, we're also going to check our 10% condition, which is going to be that n must be less than or equal to population n divided by 10. So be sure you're checking that on problems, like quiz problems that I have to grade.
Sample size has to be less than or equal to your everybody.
Population size divided by 10.
That's just 10% condition.
Yeah, so 10% condition is that you can't sample more than 10% of your population. So if you have 3,000 people, you're not allowed to go above 300.
Right. Okay.
You should check even if it doesn't ask.
You should check every time you, if you're describing your sampling distribution, you're checking your spread on your standard deviation, even if it doesn't ask. Yep. The reason being is that it affects the spread of the data. It doesn't affect the middle of the data. It affects how the data is spread out. So, why? Why? That is a fantastic question. Because if you asked, let's say you asked everyone. The 100% of your population. Then your average is going to be the exact same every time. Right? Because you're asking everyone in the population. If there are 300 people in my population, and I ask 300 people, I will always get the same average. Because I just did a census. Yes?
Yes.
So my standard deviation would be 0. There is no sway on it. There's no spread.
Okay.
Does that make sense to y'all?
Yeah.
Right? And so that means that this is a very silly equation. Because even though my n is very large at this point, I know from logic that there would be no sway on my average. The sway on that would be nothing, because I asked everyone every time, because my population size was the same as my sample size. There's nobody left off the list, and there's no way I could leave anyone off the list.
Makes sense.
Does that make sense? You guys are just kind of staring at me or the paper or the wall or something. It's kind of awkward.
That's Hannah. She
All right, shape. Shape is where we get fun.
You said fun?
Yeah. Okay, your shape is normal if ... And then we're going to break it up into 3 segments. And then we're going to put like otherwise not normal. I don't know how to put that. Like parentheses over here. Otherwise not normal. So please, I beg of you, please, do not try to write skewed. Do not try to write bimodal. Any other creative answer to show off how smart you are.
Put normal or not normal.
Just tell me if it's normal or not normal. Be great. Because you could think it's bimodal and write not normal, and it could be right skewed then, and you still get it right. Because you knew it was not normal. So just get it right. And then we're all happy. Alright. If your sample size is less than 15, it is normal only if the population, almost word pop, but I didn't. The population shape was normal and had no outliers. So if you're sampling less than 15, then it's only going to be normal if your population shape was originally normal and you had no outliers. But even one outlier, and you gotta have a sample size bigger than 15. Okay, 15 up to 30. Well, up to 29. Okay, it's gonna be normal with any shape, which is pretty nice. But what?
10%. No outliers.
But no outliers. This is like it's like throwing Bill Gates' kid, right? In the distribution of your parents' income, right? So if I did a survey of like, what's the average income of your parents? If I survey 15 of you, right? If I want it to be a normal distribution, I need to have all of you normal I need to have that distribution, the original distribution normal, and I need to have no outliers. But if I go like sample 20 of you, then it's okay if it's skewed because the distribution will become normal because I'm taking so many, but I can't have someone that's super high because if I happen to pick the super high person,
Then you'd have an outlier.
then he's gonna like stretch it far. It's gonna start to skew it, right? And on the graph, you'll definitely see that 1 point if that 1 point was chosen. Does that make sense? Mm-hmm. But n is greater than or equal to 30. It's generally agreed upon. That if your sample size is 30 or more, it's enough to water down any outliers. Yeah.
Sam.
Sampling distribution is normal. For X bar. So if your n is greater than or equal to 30, they're like, I sampled 45 people. Great. Sampling distribution is normal. I don't care what, oh, you can't see it, sorry. I don't care what the parent distribution look like. The sampling distribution will be normal. All right, so you could just take from a left skewed with some outliers that are super high. Distribution will be normal for the averages, which is really cool. Yes, yes, calm down, people.
Yay.
Yeah.
No way. I'm hungry.
But if it doesn't meet those, if it doesn't meet those qualifications,
It's not applicable.
if it doesn't meet those qualifications, what's the shape? Not normal. So pretty much what you're going to do is you're going to look to see your sample size. If it's bigger than 30, you're going to say sample size or the distribution is normal. If it's 20, 15, and 30, you're going to look for the word outliers. If they don't mention outliers, you're going to say, I think it's normal, assuming there's no outliers. Right? And if it's less than 15, you're going to look to see if there's any wording about skew or outliers. And if they don't say anything about it, you're going to say, I think it's normal, assuming the population distribution was normal and there's no outliers. So everything we talk about, like our assumptions, we're going to say, I think this is true, assuming this.
Cool.
And if it doesn't meet the condition, then you go ahead and keep working the problem. You just say this doesn't meet the condition. Like on your quiz. And something didn't meet a condition. Which I haven't seen a quiz yet that identified it. So if any of you are like, oh, I didn't find a failed condition.
How do you know when it doesn't meet it?
Like if it was on this example, if it was like sample size 10 and it says the parent distribution is right skewed, you'd say, oh, it's not a normal distribution because size is less than 15 and it's not from a normal distribution. It's from a skewed distribution. Did that adequately answer your question? You gotta see it? What's what the simulation was for yesterday? Would you like me to pull that up again? Would the simulation help now that we've taught the notes on it?
More than likely.
More than likely it would help?
Yes.
Yes, okay. See if this works. Monitor capture? Whoa. I know, right? Okay, I think I'm demonstrating this now. Plug you guys in so you can see too. Okay, so here we are, right? So if I have a sample size of 2, it's normal, right? But if I come here, well, There we go. Sample size of 2. It's not quite normal. A little hump over here, and not normal. I could go like uniform. Not normal. That's a pyramid, right? I could do skewed. That's not a normal shape, right? That's sample size 2. Maybe we have like outliers. We got a little hump there, right? A little hunchback, Notre Dame skewed thing going on. We still love you. But if you bump it up to 25, I guess we'll show you the others. Here's 5. Here's 10. It's getting there. 16. It gets thinner, you're right, and the shape is getting a little bit more normal, but it's still not symmetrical. 20. And 25. And that is pretty normal, right? And your median is pretty close to your mean, which is how we know it's not skewed.
Gotcha.
Y'all remember that when we looked at our median and our mean, and if they're the same, then they're not skewed? Yes? So with pulling 25, and if I could go up to like 50, they would start to be right on top of each other. But with like a sample size of 2, they are not. They're pretty far. Do what? Yeah, here's right over here, because this is where you have 2 from this bar.
Oh my god.
Yep. Did this help?
Yeah.
You get it now. Cool. Glad we can be of assistance.
Bear, what's your stream key?
I don't know. My stream key is, let me look it up. 4728. Yeah. Okay. Yeah, let's do baby pinky toes. I like that problem.
What? Wait, what?
Baby pinky toes. We're gonna do it. Baby pinky toes.
Pinky toe.
Yeah, it's a fun one.
I like their pinky toes.
Baby pinky toes
I like their rolls. They got rolls.
are approximately normal with an average of 0.5 centimeters with a standard deviation of 0.1 centimeters.
Wait, what mean that?
This isn't real numbers, by the way. We probably just made it up.
That's 0.5, right?
Yeah. We were like, how long do you think a baby's pinky toe is? Half a centimeter?
Half a centimeter.
Wait.
She said a foot.
A foot?
What kind of baby you see?
Oh, that centimeter's pretty long.
Babies aren't even a foot big.
I love it.
How long do you think a baby's pinky toe is? A centimeter?
Yeah.
I bet it's smaller than that.
Yeah, probably smaller than that.
Like a half centimeter?
More than a half centimeter.
I bet it's a half centimeter.
I bet it's centimeter.
When you go on your rounds, go see if you can measure a baby's pinky toe.
I'm not in that class anymore. Back to them.
When you go on your rounds, measure a baby's pinky toe. Thanks, appreciate it.
When you go to the nursery, they're all bundled up.
They're not allowed to come to the nursery anymore. They're doing weird things.
Just walk in with a ruler, say you got a project to do.
Not a measure.
I got things to do, leave me alone.
Babies are all
Break
bundled
into
up.
people's houses. Go to their babies' room.
Alright, babies are randomly selected.
That's not weird.
No.
Babies are what?
I choose you.
If you think about it, all babies are randomly selected.
Okay.
Okay.
They're working on
Alright. So we are going to find the probability a baby has a pinky toe larger than 0.68 centimeters. Little freak.
Yeah, that is long.
Do what?
Well, no, that is long if you think about it. That is kind of long to me.
It's kind of like dangling and sagging.
My cousin was mad
Mm.
That one doesn't go all the way up.
I got long toes too.
All right, so
But they're not like long though.
we're going to start moving into an RNI system. So it's going to be useful for you, and you're going to love it. You're welcome.
Thanks, Spirit.
Yep. So when we start doing problems like this, we're going to check for 3 conditions: random, normal, independent. So we're going to ask, was it random? Is the shape normal? And was it independent? Yes, a little bit. Is that good?
Yeah.
Okay. So we're going to ask, was it randomly selected?
The baby?
Yeah, well, the baby's randomly selected. So every time you work a problem, and you're gonna be drawing the curve, and you're gonna be kind of assuming it's a sampling distribution. You're an RNI check, and this will help you do the shape center spread without doing shape center spread, because you're gonna already be putting your mu, and you're already doing your standard deviation. So it gives you a format to do the things that you guys said what I wasn't asking for. Does that make sense? Like when you said, hey, you weren't asking for the 10% rule, now there's a format for it. So, yes, sir. We will. We'll plug in a normal CDF, but we're going to check our conditions, because if they didn't randomly select, if they just said, we want to find the freakiest baby ever, then the probability that they find a baby with the longest toe is better if they looked for a freaky baby than if they just randomly picked one.
What if they had a commercial saying, does your baby have like a freak baby?
Yeah, what if they put out an advertisement that said, we are looking for the ugly babies, and then they
Is your baby a freak?
is your baby a freak? Yeah, we will pay for it. And you know, you got them parents that are like, my baby's a freak, and they so was it random? So we're gonna say there was an SRS mentioned, right? So check. So it said babies are randomly selected, right? So there was an SRS mentioned. Sorry, you can't read that very well. It said mentioned. Mentioned. So we're writing. So I write R and I, and it means random, normal, independent. So there's an SRS. They talk about randomly selection, right? So you just kind of got to tell me, I see that. I see it. Normal. Okay, is it normal?
It says it's approximately normal.
Okay, so it says approx normal stated. Cool.
Check.
Check is still box.
And don't listen to commercial rally now.
Okay, and were they independent? Well, it's only how many babies are picked? How many? Wait, no. How many babies are picked?
It doesn't say.
Come on.
A baby.
I said one.
One baby.
You're lying.
Is one baby independent of itself?
Yeah.
One baby. Independent. There you go.
One baby.
Yeah, sure.
It's the American dream.
All right, so now our average is 0.5. Our standard deviation is 0.1. So now we can do this 0.5, 0.1, 0.68. Now we can do our normal CDF.
What's the arrow for?
For me to say what the proportion is,
Okay.
like the probability that the value is greater than 0.68. We're going to do this.
Dang, what's that?
0.036.
Wait. Yeah, can you?
Well, now you want it moved, you had it zoomed in. Sillies. Sillies.
I didn't have enough room for that. So.
Ain't nobody got space for these things.
My checks were too big.
Menu, normal 652. That good for you? 0.68 to infinity or something like that? Because it's 0.68 up? You could walk over and get one. All right. So let's call this A. Let's do B.
That's example A.
Oh, you can't see it. Blind children.
Oh, I know. A.
B. Okay, let's find the probability. An SRS of 3 babies.
And
Us and, yeah.
and SRS.
That's what I said.
We're just gonna put and.
Have an average. Pinky toe length of 0.55. So do you think this is going to be more common or less common to pull 3 babies and their average pinky toe length is 0.55, or to have 1 baby whose pinky toe is 0.68? Which one is going to be more common occurrence?
B. 3.
The 3 babies that have 0.55 average?
Yes.
They have to be above average together. Some of them are going to be below average.
Like we have to pull all 3 of them.
All 3 of them, and you average their pinky toes. Uh-huh.
No, the 1.
Okay. So before we check it, we're going to do R and I real quick. So R, we've already checked it up here, right? So I'll just be like not an 8.
Check. Oh.
SRS, check. If it's the first time you've done in a problem, you'll write out random, normal, independent. If it's the second time in a problem, you just do some more abbreviations. Y'all go with that? Mm-hmm. N, it says approx normal.
Check.
Check. If it didn't say approximately normal, but maybe it had a sample size of like 40, then you would just be like N is greater, 40 is greater than 30. Right? Just write something like that. Because it just, I got a confused look, so I'm going to address that. So if my sample size was 40, right? So if your sample size is 40, that's bigger than 30, and you don't care because the sampling distribution will always be normal, right?
Yes.
So you can check normal if your sampling size is greater than 30, always.
What are you looking for?
Oh, cool. Put it on my desk, please. And we'll leave on Saturday at 6 a.m.
Who are you looking for?
6 a.m.
Thank you.
She looks like she's looking for somebody.
It's going to be great.
He said.
And I,
8 weeks, yeah, you could.
independent.
I'm making eye contact with you, right?
I better survive for.
Okay, independent. Shh. So, so we're going to assume
Stupid.
independent.
Why'd you write way smaller?
I don't know. Independent. We're going to assume
What is this, writing for ants?
independent selection. Right, so we're going to assume like they're not triplets. We're going to assume they're like, okay, babies, 1, 2, 3. This is the preemie section. I don't care. Right? We're just going to say that they're independently selected. And we're also going to have to check the 10% rule.
Oh, yeah.
So we're going to assume more than 30 babies
My baby is no longer pinky toe nerves.
in the world.
Idiot.
In world.
Hospital, room, whatever you want to say.
I'm not setting a world record. My son's gonna have the longest pinky toe in the world.
How are you gonna make that happen?
I'm
Just like throwing
I'm
his
gonna
toes.
genetically engineer this little kid.
Just keep trying.
Like, it's gonna be the length of his.
Doesn't matter how much it costs. He's just going to keep having kids until he has the longest pinky toe kid ever.
Oh, man. Lucky.
Your pinky toe isn't long enough. Adoption is it.
Sad day. All right. So we're going to draw our curve. So this is for n equals 3. So we have to specify our size here, right? And the average will still be 0.5. But our standard deviation is not going to be 0.5.
Why?
Why? Because our standard deviation of x bar is going to be 0.1 divided by the square root of 3.
Oh, yeah.
Forgot about that.
Right?
Hold on.
Goodness.
Go back.
And we don't have to write the numbers
Got you.
again inside the little hump if we already have it on the other.
These are different numbers. This 0.5. Okay, she asked a good question. She said we don't have to write the numbers again. But this standard deviation is about to be a new number because this little hump is the normal curve. Hold on. This normal curve is the different normal curve from this one. This is the parent normal curve. Right? This is the normal curve of all possible averages of sample size 3.
Okay.
Yes? I really appreciated that question
But you're lying.
because I don't think you guys capture that.
Can you repeat that?
Yes. This curve right here. This is the curve of the population. This is the curve of all possible averages, sample size 3.
Okay.
This is all possible averages, sample size 3. They have the same average because the average is the average. Which is what we said as the very first line of the notes. The average is the average. But the standard deviation average is different. It's going to be 0.1 divided by the square root of 3.
It equals 0.0577.
0.577.
Yeah.
Oh, you said.
Okay? So then right here, 0.0577.
So it's gonna be your standard.
This is the standard deviation. It's not 0.1. Because this is a smaller standard deviation because I'm taking the sample from 3 babies. Right? So I would expect,
Babies, the smaller
that's right, the more babies that you take, the more trouble you're in. The more babies that you sample, the smaller that standard deviation gets because if you sample like 5,000 babies, you should expect to get really close to 0.5, right? Because it'd be very uncommon to get lots of above average babies.
or below.
Or lots of below average babies, right? Whereas if you're only taking 2 babies, 1 out of 4 times, you'll get both babies above average. 1 out of 4 times, you'll get both babies below average.
Or do you have scissors over there?
I thought you were grabbing
You need scissors?
All right, so the probability that your average is greater than or equal to 0.55 is
Yeah, put it up in the thing. Calculator.
0.55.
So scissors.
She threw scissors. See, I I don't know how
Wait,
hard to
0.55 would be right there.
Oh, actually, 0.55 would be like right
Well,
there, right?
Yeah.
Sorry. Thanks for catching it. I guess. Making me look bad.
No, no.
193? So about a fifth of the time, if you sample 3 babies, their average will be higher than 0.55.
See, I told you it'd be more common to get this one than this one.
193.
Dang it,
Okay.
I got baby.
Around the back this time.
It's fat on there.
Okay, I'm not going to check the conditions on it, but I'm just going to show you in the calculator real quick. So you don't have to write this down if you don't want to.
So, it's in the down with notes.
Yeah, you can be done with notes. Calculator zoom. Woo! Wait for it. This is such a cool idea. There you go. Then I zoom in.
It's just
I know. Like I have it perfectly centered on my computer screen so I can tell. Oh, go back. There it is, right there. Okay, so, oh, now my computer. That's not good on the stream thing. Go back to this. No, I guess we'll be here. All right, here we go. So if I go menu.
Siri, we're not talking to you.
652. Average is 0.5, 5. Oh, sorry, we can go 0.55 to 1. And my average 0.5, and this is going to be 0.1 divided by square root, parentheses. We already did 3. We'll do 3 again if you want, that's fine. Now, so I'm putting in parentheses here. Okay, so now this actually has the 3 built in. Right? And so I want to show you.
Why is it different? Wait, how did you...
Why is it different? Because I have decimal precision on my square root of 3. So now I want to show you what happens when you just move it up to like 5. You drop 6 percentage points. Right? So let's add, so if you keep adding 2,
because
I wonder if you could do that.
the more kids you have, the less, like, variance
Huh.
or whatever.
Let's try it.
What are we doing?
So what we're going to do, because Barrett feels nerdy today, do X, store it, F1 of X. Right?
I guess.
Are y'all following me what I'm doing?
Pause 1 second.
Okay, so
Why are you doing this?
look, here's what I'm doing. So I'm taking this and I'm putting it in as a function. Okay? So what it's going to do is then I'm going to go to a table in the graph and I'm going to look at how my sample sizes changes and how it changes with my different sample sizes.
Okay,
It'll be nifty.
that makes sense.
Yeah, there you go.
Done.
Done. Yep, that is done. We like that. Let's see if we can put it in a spreadsheet. I've never done this before. This will be fun. Yeah, what if it doesn't work? I really like your attitude. Thank you.
I think it's gonna be great, Barry.
Menu.
She was still trying to get this thing on this calculator.
How do I show table? Oh, F1. Escape. Go back. I want F1. Enter.
Wait, what did you...
Look at that. Wow. Menu. Table. Split screen table.
Oh, wow.
Barrett, I'm going to the back.
Okay. Now look at this. Shh. Okay, so if I have a sample size of size 1, what is my probability of getting better than 0.55?
0.30.
0.3, right? 31%.
Yeah.
And then if I sample 2, it drops 7 points
24.
to 24%. Yes?
Yeah.
And if I add another kid, I drop about 5 points to 19%. Right?
Yep.
Y'all follow me?
Yep.
If I add another point, how much do I drop now? I'm going from 19 to about 16, so it's going to be how much? 3%? Hold on. We're going to go down. 16 to 13 is 3%. 13 to 11 is 2%, right?
Another 2%.
11 to 9 is another 2%.
Then it's 1.
And then we're going down to 1, 9 to 7, 7 to 6, and then 4. And so then we're getting to like 4. We're getting to on like 11 and 12. It looks like it's 0.7. So we're getting close to like 0.5%, right? Yeah. And you notice that each additional kid that we sample is giving us less and less return, right?
Yeah.
We're getting diminishing returns on this.
What is diminishing returns?
Means that more, if I do a little bit more work when I've done just a little bit of work, I get really good effort.
Okay.
But if I do a little bit more work when I've done a lot of work, get just a little bit. It's like when you've done a project and you say, this will be a 95. And if I want to get 100, I got to put like 2 more hours in.
Oh.
And you're like, is it worth the effort? But if you haven't started the project, and you say, hey man, how hard will it be for me to get a 70? And your friend says, it'll take about 2 hours to get a 70, right? So at that point in time, you've done nothing. Takes 2 hours to get a 70. And so for the person who has a 0, 2 hours gets them 70 points. And for you, 2 hours gets you 5 points, right? It's diminishing returns. The less you have.
That makes sense.
Yeah.
Okay.
So, and you'll just notice that that pattern continues. It's less and less profitable the more samples you take. Isn't that crazy?
Yeah.
Amazing.
Y'all ready to be done now, right?
Yes, sir.
Okay.
Was that it for the lesson?